The atom is empty. Not mostly empty, empty. The nucleus is so small relative to the atom that if you blew the whole thing up to the size of a football stadium, the nucleus would be a grain of sand sitting at the 50-yard line. The rest, nothing, which means the chair you're sitting on right now is almost entirely nothing, and yet it holds you up. If that doesn't bother you, it should, because here is the question nobody asks loudly enough. If matter is mostly empty space, why does anything feel solid? Why doesn't your hand pass through the table? Why does the universe bother holding itself together at all? These are not philosophical questions dressed up in science clothing. These are hard, specific, physical questions, and the answers, when you actually dig for them, are stranger than anything you were told in high school. So let's dig. Start with what you think you know. You've been told the atom has a nucleus, protons and neutrons packed together, and electrons orbiting around it, like a miniature solar system. Clean, intuitive, wrong. Not wrong in a minor, technical, let's not get into it way. Wrong in the way that matters. Wrong in the way that changes what you think the universe is made of. The solar system model was proposed by Ernest Rutherford in 1911, and it was a genuine breakthrough for its time. Rutherford had just done one of the most elegant experiments in the history of physics, firing alpha particles at a thin sheet of gold foil and watching where they went. Most went straight through, a few bounced back, and Rutherford said famously that it was as surprising as if you fired artillery shells at tissue paper and they came back and hit you. That bounce back told him the atom was mostly empty, with a tiny dense nucleus at the center. That part was right. The solar system picture that came with it, electrons orbiting like planets, that part was a disaster waiting to happen. Here's why. If you have a charged particle moving in a circle, it accelerates. Acceleration means it radiates energy. Radiation means it loses energy. Lose enough energy and the electron spirals inward, crashes into the nucleus, and your atom collapses in about 10 to the minus 11 seconds, which means if the solar system model were correct, you and everything around you should have ceased to exist roughly 10 picoseconds after the universe formed. The fact that we're all still here is, in a very literal sense, proof that something is deeply, fundamentally wrong with that picture. Niels Bohr fixed it, or rather, he patched it in 1913. He said electrons don't orbit just anywhere. They occupy specific allowed orbits, specific energy levels, and they cannot radiate when they're sitting in one of those levels. They can only emit or absorb energy when they jump between levels, and they do it in discrete chunks, quanta. It worked. The numbers matched. The spectral lines of hydrogen came out right to 4 decimal places. And everyone should have immediately asked, why? Why are only certain orbits allowed? What is the physical mechanism that enforces this rule? Bohr didn't know. He was honest about that. He had a recipe that worked, and he had absolutely no idea why it worked, and he knew it. That's the situation in 1913. You have a model that produces the right answers for reasons nobody understands, describing a structure that makes no physical sense under classical mechanics. And the response of the physics community was essentially, let's keep going and hope the picture clarifies. It did not clarify. It got stranger, far stranger, because 12 years later, a young Frenchman named Louis de Broglie wrote his doctoral thesis suggesting that if light can behave like a particle, which Einstein had shown in 1905, then maybe particles can behave like waves. His advisor thought it was insane. He sent it to Einstein. Einstein said it looked interesting. De Broglie got his degree. And then Davison and Germer shot the electrons at a crystal lattice and watched them diffract the same way light diffracts, the same way waves diffract, and the whole game changed. The electron is a wave. Not metaphorically, not sort of. When it is not being measured, it genuinely, physically propagates like a wave. It spreads out. It interferes with itself. It goes through 2 slits at once. And the moment you measure it, the moment you ask where it is, it collapses to a point. it becomes a particle. It gives you a location, a single definite position, as if it had been there all along. But it wasn't. The wave was real, the spread was real. The interference pattern you see building up one electron at a time on a detector screen that is not a statistical artifact, it is not a measurement error, it is not a failure of equipment, it is the universe telling you something fundamental about what an electron actually is. And here is where it gets strange in a way that cannot be walked back. Run the double slit experiment with one electron at a time, fire a single electron at the two slits. It has no partner to interfere with. There is nothing else in the apparatus. And yet, if you run the experiment long enough, firing electrons one by one, the pattern that builds up on the detector is an interference pattern. Bright bands and dark bands, exactly where the math predicts if each electron somehow goes through both slits simultaneously and interferes with itself. Cover one slit, the pattern disappears. Uncover it, the pattern returns. The electron alone, with nothing else present, behaves as if it knows both slits exist and chooses a landing point based on that information. How? Through what mechanism? There is no mechanism. There is mathematics, beautiful, precise, infuriating mathematics, and there is no underlying picture of what is physically happening that everyone agrees on. Not then, not now. Richard Feynman said, and I think he meant it completely, that nobody understands quantum mechanics. He didn't mean it as modesty. He meant it as a precise statement about the state of the field. We know how to use it. We know what it predicts. We know it is right. We do not know what it is saying about the nature of reality. Now let me tell you about something called the wave function, because it is the central object in quantum mechanics, and most popular accounts of it are charitably incomplete. The wave function, typically written as the Greek letter psi, is a mathematical object that encodes everything there is to know about a quantum system. For a single electron, it is a complex valued function of position and time. Complex valued means it has a real part and an imaginary part. It takes values in the complex numbers, not just a real line. You cannot directly observe the wave function. What you can observe is related to its square. The square of its amplitude gives you the probability of finding the electron in a given location if you measure it. This is the Born rule proposed by Max Born in 1926, and it is arguably the most important interpretational step in the history of quantum mechanics, and it came completely out of nowhere, theoretically. There was no derivation. Born looked at the mathematics, looked at what the experiments were showing, and said, I think the square of this thing gives probabilities. And he was right. And nobody has ever satisfactorily explained why. The wave function for a single electron in a hydrogen atom is not a little cloud sitting around the nucleus. It is a precise mathematical function that tells you for every point in space the probability amplitude of finding the electron there. Some of those functions, the ground state, the excited states, have names and shapes. S orbitals, P orbitals, D orbitals. You've probably seen the pictures. Fuzzy blobs, dumbbells, clover leaves. These are real. These are not artistic interpretations. These are actual probability distributions calculated from the Schrödinger equation, confirmed by experiment, and inside those blobs, the electron is not traveling along any path. It does not have a path. It is in a superposition of all positions simultaneously weighted by the wave function until you look. That last sentence is the one that caused 50 years of argument among the greatest physicists who ever lived. Einstein hated it. Not because he was old and conservative. Einstein had been the most radical thinker in physics for 2 decades at that point. He hated it because it seemed to imply that physical reality was not well defined until observed, that a particle does not have a position until measured, that the act of measurement was somehow bringing things into existence. And Einstein said, in the most famous complaint in the history of physics, does the moon exist when nobody is looking at it? He was asking a real question. He wasn't being rhetorical. He was asking, is quantum mechanics a complete description of reality, or is it a useful but incomplete tool that obscures some deeper, fully determined reality underneath? He and Bohr argued about this for decades. Two of the most brilliant men who ever lived, arguing in hotel lobbies, in conference rooms, and in letters across the Atlantic about what the theory was actually saying. They never resolved it. Einstein died in 1955, still convinced that quantum mechanics was not the final word. Bohr died 6 years later, equally convinced that it was. I want to be honest with you about where I stand. I think quantum mechanics is not going anywhere. The evidence is overwhelming, the predictions are perfect, and every attempt to build a hidden variable theory underneath it has run into walls, most famously the Bell inequality experiments, which I'll get to. But I also think that the measurement problem, the question of why and how the wave function collapses when we observe a system, is a genuine open problem and not a solved one. Anyone who tells you it's solved is telling you which interpretation they prefer. That's not the same thing. Let me take you deeper into the atom, because we haven't gotten to the really strange part yet. Hydrogen is simple. One proton, one electron. The Schrödinger equation handles it exactly. But go to helium, 2 protons, 2 neutrons, 2 electrons, and something new happens. The wave function of the 2-electron system is not simply 2 separate wave functions multiplied together. It is a single wave function defined over the combined configuration space of both electrons simultaneously. This is called entanglement, and it is not a special exotic phenomenon that requires extraordinary conditions. It is the default. It is what quantum mechanics always does when you have more than one particle. The electrons in a helium atom are entangled with each other. Their properties are correlated in a way that cannot be explained by any local classical mechanism. Here is what entanglement actually means. Stripped of the mysticism that gets attached to it, take 2 electrons and put them in a specific quantum state called a singlet state, a state where their spins are correlated such that if you measure one and find it spinning up, the other will be spinning down, and vice versa, with certainty. Now, separate them. Take one to New York and one to Tokyo. Measure the one in New York. You get a result, say, spin up instantaneously, not after some light travel delay. Instantaneously, the state of the Tokyo electron is determined. It will be spin down. You didn't do anything to the Tokyo electron. You didn't send a signal. But the correlation is there, and it is perfect. Einstein called this spooky action at a distance and argued it proved quantum mechanics was incomplete, that there must be hidden variables, pre-existing information carried by the electrons from the moment they separated, that determines the outcome in advance. It's a completely reasonable thing to argue. It's also wrong. John Bell proved it was wrong in 1964. Not philosophically wrong, mathematically experimentally wrong. Bell derived an inequality, a mathematical constraint that any theory with local hidden variables must satisfy. Quantum mechanics predicts violations of this inequality. And in the 1980s, Alain Aspect and his collaborators in Paris performed the actual experiment and found exactly what quantum mechanics predicted. The violations were real. Local hidden variables are ruled out. The correlations between entangled particles are not explained by shared information stored at the source. They are a genuine non-local feature of the quantum state. Now, this does not mean you can send information faster than light using entanglement. You can't. The individual measurement outcomes are random. You can't control what result you'll get in New York, so you can't encode a message in it. The correlation only becomes visible when you compare the two results, which requires a classical signal that travels at or below light speed. Relativity is safe, but the non-locality is real. The universe is non-local at the quantum level in a way that is precise and measurable and cannot be explained by anything local happening underneath. That should shock you. It still shocks me. Now let me go one level deeper, because we have been talking about electrons and wave functions, and there is a whole layer of reality underneath that most people never see clearly. Go inside the nucleus, inside the proton. This is where things stop being strange and start being violent. A proton is not a fundamental particle. It is made of quarks specifically, 2 up quarks and 1 down quark, bound together by the strong nuclear force. The carriers of the strong force are called gluons, and here is where the story gets genuinely bizarre. The quarks inside a proton are never free. You cannot pull a quark out of a proton and hold it in your hand. Try to separate them, and the energy you pour in goes into creating new quark-antiquark pairs from the vacuum, and you end up with more particles, not isolated quarks. This phenomenon is called confinement, and we have never observed a free quark. We have excellent theoretical reasons for thinking confinement is real. We have simulations that support it, a rigorous mathematical proof, still waiting. The Clay Mathematics Institute will give you $1 million if you can prove confinement from the mathematics of quantum chromodynamics. Nobody has collected. There's something else happening inside that proton that I want you to think about carefully. When you probe the proton at high energies, when you smash it with electrons, in the kind of deep inelastic scattering experiments we did at SLAC in the late 1960s and 1970s, you find that it's not simply 3 quarks. It's 3 quarks swimming in a sea of virtual quark-antiquark pairs and gluons, all popping in and out of existence on timescales so short they're permitted by the Heisenberg uncertainty principle. The proton is not a static object. It is a churning, dynamic, probabilistic storm of interacting fields. Most of the proton's mass doesn't come from the quarks. The bare quark masses account for only a few % of the proton mass. Most of it comes from the binding energy, from the kinetic energy of the quarks bouncing around, from the gluon field energy. Mass, the thing you put on the scale, the thing that tells you how hard something is to accelerate, is mostly not in the stuff. It's in the interaction. It's in the field. Einstein's E equals mc squared cuts both ways. Mass is a form of energy, and the energy of the interaction is part of the mass of the system. This is something I find genuinely staggering every time I think about it carefully. Pick up a rock. Almost all of the weight you feel in your hand is not the mass of quarks. It is the energy of the strong force binding quarks together inside protons and neutrons. You are holding captured field energy. That's what solidity is. That's what weight is. Let me stop here and tell you about a conversation I had a long time ago, not a formal debate, just a late-night argument with a colleague after a conference about what we were really learning from the deep inelastic scattering experiments. The question on the table was whether the partons we were seeing, the point-like constituents Feynman was calling them, were actually quarks in the sense Gell-Mann had proposed, or whether they were something else, something we didn't have language for yet. What struck me even then was that the question wasn't really about quarks. It was about whether our habit of thinking in terms of particles, localized, countable, individual things was the right framework at all, because the data kept refusing to behave the way particles should behave. The constituents looked like particles when you hit them hard. They looked like waves when you left them alone. They acted like they had no fixed position inside the proton until you poked them. And every time you thought you had a clean particle-like picture, something would happen to smear it back out. The question I kept coming back to, and still come back to, is whether the particle picture is fundamental or whether it's a derived concept, something that emerges from a deeper description that is entirely about fields and quantum states and has no particles in it at all. Quantum field theory leans hard in that direction. In quantum field theory, particles are not primary. Fields are primary. The electron is not a little ball. It is a localized excitation of the electron field which permeates all of space. The photon is a localized excitation of the electromagnetic field. The Higgs boson is an excitation of the Higgs field. The particles are what fields do when they are disturbed. They are not the bottom layer. And here is where the connection to something vast becomes unavoidable. If particles are excitations of fields, and fields permeate all of space, then the vacuum, empty space, the nothing between things is not nothing. The quantum vacuum is a seething, fluctuating state of all the quantum fields simultaneously sitting in their lowest energy configurations, but subject to quantum fluctuations that briefly drive them away from that minimum. Virtual particles pop in and out of existence in the vacuum on timescales allowed by the uncertainty principle. The vacuum has energy, the vacuum has structure. The vacuum is not nothing. We know this experimentally. The Casimir effect takes two uncharged metal plates and put them very close together in a vacuum. They attract each other. Not because of gravity, not because of static electricity, but because the vacuum fluctuations outside the plates have more modes available to them than the fluctuations between the plates. And this asymmetry produces a net inward force. It is measured. It is real. It is a force generated by nothing, acting on nothing. And here is where I have to be honest about something that keeps a lot of us up at night. Quantum field theory predicts a vacuum energy density. Cosmology tells us the universe has a vacuum energy density. We call it the cosmological constant, or dark energy, and we can measure it from the acceleration of the expansion of the universe. The theoretical prediction and the measured value disagree by somewhere between 60 and 120 orders of magnitude, depending on how you do the calculation. This is the worst prediction in the history of physics, not a little bit wrong, catastrophically, grotesquely, embarrassingly wrong, and nobody knows why. If you go to any honest physicist and ask them what the cosmological constant problem is telling us, they will tell you it is telling us that something fundamental is missing from our understanding, not a technical detail, something fundamental. I am not going to stand here and pretend this is a solved problem. It is one of the most unsolved problems in all of science. And it connects directly to everything we've been talking about, to the nature of the quantum vacuum, to what empty space actually is, to why atoms exist and why they have the properties they have. The fine structure constant, the number that determines the strength of the electromagnetic interaction, that sets the scale of atomic physics, that determines the size of atoms and the energies of chemical bonds, has the value it has, approximately 1 over 137, and nobody knows why. Not in the sense of not yet knowing, in the sense that there is no argument from deeper principles that forces it to be that value rather than some other value. Feynman called it one of the greatest mysteries in physics. It still is. The atom sits at the center of a web of open questions that run in every direction, downward into quarks and quantum fields and the structure of the vacuum, upward into chemistry and biology and the structure of matter, sideways into the foundations of quantum mechanics itself, into the measurement problem, into the nature of the wave function, into what it means for something to be real, and outward into cosmology, into why the constants are what they are, into why the vacuum energy is what it is, into why there is something rather than nothing. I want to come back to something I said at the beginning, because I don't think I pushed it far enough. The chair holds you up. The solidity is real, but now you know what that solidity actually is. It is not little hard balls packed together, resisting your weight. It is the Pauli exclusion principle, the quantum mechanical rule that no two electrons can occupy the same quantum state, simultaneously preventing the electron clouds of neighboring atoms from merging. It is the electromagnetic repulsion between those electron clouds. It is the zero-point motion of electrons, which quantum mechanics requires them to have even in their lowest energy state, preventing them from collapsing to the nucleus. Everything solid, every surface you've ever touched, every floor that has ever supported your weight, every wall that has ever stopped you, is held up by quantum mechanics, by the same strange, non-local, wave function collapsing, interference-generating quantum mechanics that we've been discussing this whole time. Without it, matter would collapse. Without the Pauli exclusion principle specifically, there are no stable atoms, no chemistry, no biology, no you. The exclusion principle was proposed by Wolfgang Pauli in 1925, and it came before anyone had a good theoretical reason for it. And Pauli just looked at atomic spectra and said, the data requires that no two electrons occupy the same state. It was pure phenomenology. The theoretical justification came later from the full machinery of quantum field theory, and it turns out the exclusion principle for fermions is deeply connected to the spin statistics theorem, which connects the spin of a particle to its quantum statistical behavior, and which follows from combining quantum mechanics with special relativity. Pauli himself proved the spin statistics theorem in 1940, and he described it as one of the most difficult results in all of physics to derive properly. He was right. The theorem says that particles with half-integer spin, electrons, protons, neutrons, quarks, obey Fermi-Dirac statistics and cannot share quantum states. Particles with integer spin, photons, gluons, the Higgs boson obey Bose-Einstein statistics and actually prefer to share quantum states. This is why lasers work. This is why superfluidity exists. This is why the periodic table has the structure it has. All of it, the whole architecture of matter and its interactions, flows from the relationship between spin and statistics, which itself flows from the unification of quantum mechanics and relativity. People sometimes ask me what the most beautiful result in physics is. I have different answers on different days, but the spin statistics theorem is always in the conversation because it connects two things that look like they have nothing to do with each other: the intrinsic angular momentum of a particle and the way it shares space with identical copies of itself and shows that they are, at a deep level, the same fact about the universe, that the universe has a coherent internal logic that forces these things to align, that you don't get to choose them independently. I've spent a lot of time in this talk describing what we know. Let me spend a few minutes on what we don't, because I think it's more important. We do not have a satisfactory interpretation of quantum mechanics. This is not a fringe position, the Everett many worlds interpretation, the Copenhagen interpretation, the de Broglie-Bohm pilot wave theory, the relational interpretation, cubism. These are not competing scientific theories in the sense of making different experimental predictions. They largely agree on predictions. They disagree on what is actually happening, on whether the wave function is real or just a calculational tool, on whether there is a collapse, and if so, what causes it, on whether the observer plays a fundamental role or is just another quantum system. These are not settled questions. There are serious physicists who hold each of these positions. I have my own views, which I hold with moderate confidence and have revised more than once. We do not understand quantum gravity. General relativity describes space-time as a smooth, curved manifold. Quantum mechanics describes matter and energy as discrete, probabilistic, subject to superposition and entanglement. These two descriptions work extraordinarily well in their respective domains. When you try to combine them, when you try to describe what happens at the Planck scale, at the center of a black hole, at the moment of the Big Bang, the mathematics breaks down. You get infinities that cannot be removed by the renormalization techniques that work in quantum field theory. String theory is an attempt to fix this. Loop quantum gravity is another attempt. Neither is confirmed by experiment. Both are, in my honest assessment, still speculative frameworks. However sophisticated, we do not have a working theory of quantum gravity. I spent the better part of 30 years working on the black hole information paradox, the question of whether information is destroyed when matter falls into a black hole. I argued against Hawking for decades. Hawking said information is lost. I said information cannot be lost, that it must come out somehow with the Hawking radiation. Eventually, and this took a long time, longer than I'd like to admit, most of the community came around to the view that information is preserved, that Hawking's original calculation was missing something. Hawking conceded the bet in 2004. The resolution, through the lens of the holographic principle and the ADS CFT correspondence developed by Maldacena, points to something profound about the relationship between quantum information and space-time geometry. The information about everything that falls into a black hole is somehow encoded on its horizon, a two-dimensional surface. Encodes all the information about a three-dimensional volume. This is the holographic principle, and it is one of the deepest things we know about quantum gravity, and we still don't fully understand it. But here is what I want you to take from that. The question that started that whole battle, what happens to information inside a black hole, is directly connected to quantum mechanics at the atomic scale. The reason information can't be destroyed is unitarity, the requirement that quantum mechanical evolution preserves information, that the total probability always sums to 1, that the wave function evolves in a completely reversible way. This is a property of quantum mechanics that we test in atomic and particle physics experiments every day. And that same principle, extrapolated to black holes in space-time, leads to a profound constraint on the nature of gravity and the structure of space-time. The atom and the black hole are connected by the same thread. Quantum mechanics is not just the theory of the small, it is the theory of everything, and we are still learning what it says. So here is where I want to leave you. You came in here knowing the atom was mostly empty space. You probably thought that was the strange part. It's not. The empty space is the least of it. The strange part is that the stuff that isn't empty, the nucleus, the electrons, the fields, doesn't work the way anything in your everyday experience works. It doesn't have definite properties until measured. It doesn't travel along definite paths. Two electrons on opposite sides of the planet can be correlated in ways that have no classical explanation. The vacuum is not nothing. The mass you feel when you lift a rock is mostly the energy of the strong force. The hardness of every surface is quantum mechanics refusing to let electron states overlap. The periodic table, the whole structure of chemistry, the whole platform on which biology runs, is the consequence of a theorem connecting spin and statistics that follows from uniting quantum mechanics with relativity. And underneath all of this, holding it all up, connecting the atom to the black hole to the structure of space-time, is a mathematical framework that is spectacularly successful and genuinely not fully understood. Not in the sense of needing more data, in the sense of needing better concepts. Concepts we don't have yet. Concepts that some person in this room or some person who will be inspired by a conversation they have with someone in this room might someday find the atom is empty. What fills it is stranger than the emptiness, and we are nowhere near the bottom of it.